Good evening, dear attendees. Thank you for joining us today for this amazing talk. Uh, Today we are fortunate to have Professor Hai Hansun ma'am with us today. And let me quickly introduce her to you all. So, Dr. Hai Hansun is an assistant professor at the Department of Electrical and Computer Engineering at the University of Wisconsin-Madison. She received her BE degree from the Beijing University of Posts and Telecommunications in 2015 and her PhD from the University of Technology, Sydney in 2019, both in electrical engineering. She was a postdoctoral research fellow at Nanyang Technological University from 2019 to 2023. Her research focuses on advanced antenna system for next generation wireless communications, intelligent electromagnetic sensing, and non-destructive testing technologies. Dr. Sun was the recipient of Young Professionals Paper Honorable Mentions at the 2022 International Symposium on Antenna and Propagation, the Best Student Paper Awards at the 2019 Australian Symposium on Antennas and 2018 Australian Microwave Symposium, and an honorable mention in the Student Paper Competition at the 2018 IEEE International Symposium on Antenna and Propagation. She was awarded the Moshgan Danishmand Grant for Women by the IEEE Antennas and Propagation Society in 2021. She is an associate editor for the IEEE Antennas and Wireless Propagation Letters and the IEEE Open Journal of Antennas and Propagation and serves as the IEEE APS YA Professional Ambassador. Welcome, ma'am. Welcome to this talk, and thank you for joining us.
Thank
Ma'am,
you.
you can start the talk.
Yeah, sure. Can you hear me?
Yes, ma'am, we can hear you.
Yeah, great. Thank you for the great induction and thank you for having me here. It's my great pleasure to join all of you today. Hi everyone, I'm Hai Han and I'm an assistant professor at the University of Wisconsin-Madison. Today I will share how we can use advanced ground-penetrating radar technologies to explore the fascinating subsurface world. This talk is associated with IEEE Antenna and Propagation Society Young Professionals Program. So before we get started, I would like to briefly introduce IEEE Antenna and Propagation Society and the IEEE Young Professionals. As you probably all know, the field of interest of Antenna and Propagation Society are the antennas, electromagnetic wave radiation propagation, and all the applications and systems associated with them, including the wireless, mobile, satellite, and telecommunications. Some quick facts about IEEE Antenna and Propagation Society. We have more than 10,000 members, including more than 1,000 student members, which is great. We have 6 journals for the conferences, and we have many IEEE fellows, life fellows, and offer a wide range of paper awards, field awards, and fellowship opportunities, which I'll introduce slightly later. IEEE Young Professionals is a group of IEEE members or volunteers who have graduated from their first professional degree within the past 15 years. If you are a graduate student, a postdoc fellow, whether you work in academia or industry, you can definitely join as part of the IEEE Young Professionals. And I believe a lot of you are students, and I believe we have many students in our chapter. So if you already is an IEEE student member, you can join IEEE Antenna and Propagation Society with student membership fee of just $1. You probably want to know, why should I join the Antenna and Propagation Society, right? Well, we offer a wide range of membership benefits. The first one is that you have access to all the IEEE Antenna and Propagation Society journals. We have 3 principal legacy journals: the IEEE Transactions on Antenna Propagation, Antenna Propagation Letters, APL, the IEEE Antenna Propagation Magazine. And we have an open access journal, which is IEEE Open Journal of Antennas Propagation. And we have 2 new journals joined with other societies, which are the IEEE Journal on Multiscale and Multiphysics Computation Techniques, and IEEE Journal of Electromagnetics, RF and Microwaves in Medicine and Biology. Besides having access to all these journals, we offer a wide range of fellowship opportunities, grants for young professionals. For example, we have research scholarships for undergraduate researchers, and we have fellowship opportunities for both predoctoral and doctoral researchers. And we offer the Best Paper Awards as well as Mid-Career Distinguished Achievement Awards for young professionals. If you are going to attend IEEE APS conference, the Antenna Propagation Society also offers a wide range of travel support for young professionals and graduate students, and all of them are listed here. If you want to know a complete list of awards and fellowship opportunities, please look at the link here. I would say Internal Propagation Society provides numerous opportunities and supports for students and young professionals. So it would definitely be great to be part of the society. The committee members for IEEE Internal Propagation Societies and Professionals this year are shown here, and we have 12 young professional ambassadors this year, and I'm very honored to be one of them. The IEEE Internal Propagation Society Young Professionals have won a lot of awards. If you want to know more about that, please feel free to visit this link and follow us on the LinkedIn pages. We will be delighted to have you there. Okay, now let's go back to the topic today. So today we are going to talk about how we can use advanced ground-penetrating radar technologies to see beneath the surface. Well, imagine being able to see beneath the surface. There are so many things we can do, right? We can easily tell the health condition of our building, utility, plants. We can find a hidden cave in World Heritage Site without any excavation. We can measure the depth of glacier with minimal labor work in the freezing temperature. All of them sounds great, but the question is, how can we see beneath the surface? Well, ground-penetrating radar is a non-destructive tool that uses electromagnetic waves to inspect subsurface environment. If we use an antenna if we use ground-penetrating radar, or in short GPR, to scan an area, the transmitting antenna sends out electromagnetic waves into the ground. When the wave hits a varied object with different electrical material properties, the wave will be reflected back to the surface and acquired by the receiving antenna. At one antenna location, we'll receive the reflect signal as a function of two-way travel time and signal amplitude. We call it as a one-dimensional A-scan. In this case, we'll observe two main reflections. One is the surface reflection coupled with the antenna crosstalk, and we'll have the object reflection shown here. The distance from the object to the soil or the surface can be calculated based on the two-way travel time and the propagation velocity of electromagnetic waves in the subsurface medium. And the power of this reflex signal from the object is governed by the well-established radar equation. Is a complex function of the transmitting system, receiving system, signal loss at the air-to-ground interface and along the propagation path, the object radar cross-section, as well as any polarization mismatch in the wave transmission and reflection process. If we move the GPR along a scanning trace, then its scans at different locations will be further compiled into a two-dimensional radargram, and we call it as a two-dimensional B-scan. In the two-dimensional B-scan, the horizontal axis denotes the antenna position, the vertical axis denotes the two-way travel time, and different colors shows different signal amplitudes. Well, along the scanning trace, as we can say, the GPR first moves closer to the object and then moves away from the object. So the delay time from the signal object first decreases and then increases. So the object reflection typically shows a hyperbolic pattern in the two-dimensional B-scan. And this reflection signature contains abundant information of subsurface object. If we could analyze that, we could derive key parameters from the object and improve our understanding of subsurface object. And if we want to scan multiple parallel traces around an area, the two-dimensional B-scans will be further compiled into a three-dimensional C-scan. And we can see object signatures shown here. If we could analyze the C-scan signals, we could derive three-dimensional parameters of the object, and we can even reconstruct three-dimensional subsurface scenarios. GPR is definitely not a new technology. It has a long, rich, and fascinating history spanning across different disciplines over the past century. I read some stories online, and it turned out that the GPR technology can be dated back to 1904 when a German engineer, Christian Hosmeyer invented the early form of the radar to detect distant metallic objects. Then 6 years later, 2 German scientists patented the first use of continuous wave radar to locate buried objects. Then later on, Dr. Hilsenbeck patented the first use of pulse technique to detect subsurface structures, which greatly improved the depth resolution. And for the next 30 years, ground-penetrating radar were mainly used to probe the depths of ice, glacier, and fresh water, as these are the ideal medium for the electromagnetic wave transmission. Then the turning point came in 1974 when NASA launched the Apollo 17 mission, uses a GPR unit to study the moon's surface profile and interior structures. And this kind of historic moment really brought GPR into a wide attention and triggered widespread applications of GPR. For the next 20 years, GPR has been utilized in many different fields, for example, in civil engineering to locate voids, tunnels, cables, in geotechnical engineering to explore underground mineral resources, in archaeology to find buried structures, caves, and in military to detect tunnels, landmines, and landmines to save human life. In recent years, we have witnessed great advancement in GPR technologies thanks to the rapid evolution of electronic hardware and computational power. And we have witnessed widespread use of GPR for subsurface sensing in various disciplines, for example, for planetary exploration associated with this rover. This is truly exciting. Despite the widespread use of GPR in numerous applications, we still had we have seen several challenges in many GPR applications. For example, when we look at the radargram shown here, you can see that the object buried at a deep location may not be well detected in the GPR radargram due to the attenuation in the lossy surface environment. So to guarantee the penetration depth and resolution of objects of different characteristics at different positions, we have to further advance low-frequency, ultra-wideband, and high-gain GPR antennas. Then, from the radargram shown here, we can say that irregular and complex subsurface environment inevitably introduce a dominant subsurface clutter, which disguise or distort subsurface reflections, especially for object which is very close to the soil. And this clutter interference greatly challenges the target identification and further characterization. So how to remove the clutter interference and restore the target responses has been a long existing problem in the GPR applications. And then once we collect GPR radiogram, how can we use the object signatures in the GPR radiogram to characterize subsurface object? For example, the object size, material orientation. This will greatly help us to improve our understanding of the subsurface object. And is there a way to map the subsurface environment with high resolution? This is the ultimate goal for us to visualize the subsurface environment, right? So all of these challenges calls for advanced data processing and image algorithms, and our research has been devoted to address these challenges. So first, to improve the detection capability of objects of different characteristics at different depths, we have invented and tailored multiple dual-band antennas and compact arrays to well detect objects in different specific applications, which I'll introduce later. A common feature of these antennas are that they all have broad low-frequency bands over 4 GHz. The frequency band generally range from below 1 GHz to above 4 GHz. And these antennas enjoys great port isolation and have high antenna gain, which guarantees the penetration depth, resolution, and polarization purity of the ground-penetrating radar system. These antennas are specially tailored to have a compact size, so we can easily implement them in the portable GPR system. Once we design antennas with high performance characteristics, we have used them to collect radargrams in many different applications. Next question arises, that is, how can we remove the environmental clutter and restore the target responses, right? This will really help us to improve object identification accuracy and further object categorization. Well, when we look at the raw radiogram shown here, it's pretty clear that object reflections shown as horizontal bandings, as we analyzed earlier, and the environmental clutter shows as kind of like horizontal bandings, not really uniform, but like relatively uniform. So they show as horizontal bandings in the GPR scans. So a feasible method would be to capture these hyperbolic features corresponding to object reflections and remove other features corresponding to environmental clutter. How can we achieve that? Well, convolutional neural network architecture has great feature extraction capability and learning capability. So it could be a great method to solve this clutter removal challenge. But how can we leverage advantage to remove clutter and restore target responses in diverse subsurface scenarios? To answer this question, we carried our study in three steps. So first, convolutional neural network architecture. Convolutional neural network is a data-driven deep learning method. So if we wanted to work well in diverse subsurface environment, we have to train it with a suitable dataset with diverse distribution of clusters, right? So first, we built the very large-scale dataset that contains randomly distributed robot cluster for network training. Our dataset includes three subdatasets: one synthetic subdataset and one sand subdataset and concrete subdataset collected in the field. For each subdataset, we adopted different GPS systems to collect diverse cluster distributions in different subsurface environment. The different GPS system and different subsurface environment offer a rich diversity of cluster distributions in our dataset, which greatly improve the generalizability of the data-driven methods. With the same dataset, the network performance largely governed by the network architecture and the loss function that drives the network optimization. So next step, we need to build a suitable neural network architecture to effectively remove clutter and restore target responses. Well, firstly, we adopted the classic UNet architecture as shown here, which includes the encoder, decoder, and skip connections between them. But we found out that directly borrow this neural network architecture cannot achieve promising results because the feature maps in the encoder, especially these low-level feature maps, still contain abundant clutter information that has not been suppressed. If we directly concatenate these features to the decoder, it will result in unsatisfactory clutter removal performance, which is what we don't want. So we further integrate residue dense blocks along the skip connection link to purify the features, to adeptly preserve the features related to object reflections and suppress features related to environmental clutter. And then we pass this purified feature to the decoder and to reconstruct the clutter removed radiogram. And this introduction of residue dense block greatly promotes network's capability to remove clutter and further restore the target responses. Once we build this neural network architecture, the final network performance depends on the loss function that drives the network optimization. Given a raw radiogram, the network predicts a clutter-free radiogram, and the loss function numerically evaluates the difference between the output image of this neural network with the ground truth cluster-free radiogram, and it backpropagated to update neural network architectures. The optimization of network is to optimize this loss function, or in other words, the network learns to predict an image that highly resembles this clutter-free radiogram. In our study, we our loss function is composed of the mean absolute error loss and the multi-scale structure similarity loss. We experimentally found out that these two loss functions complement each other. The mean absolute error loss compute the numerical difference between these two images, while the multi-scale structure similarity loss compute the visual difference of these two images in terms of the luminance, contrast, and structure similarity. So we found out that these two loss functions complement each other and better drive the network optimization for this specific task. The well-trained neural network has been used to remove clutter and restore target responses in many different real-world cases. Some of the results are shown here. For the first case, we have a metallic can buried in the soil. For the second and third cases, these are the metal bars in reinforced concrete buildings. We can say in the raw radagram that we collected, the dominant background environmental clutter disguises the object direction, especially in the second and third cases. And it makes it very hard to extract object reflections for further object identification. But we can say that our neural network is capable of successfully remove all the environmental clutter and restore the target responses with high accuracy. And this greatly facilitates further object categorization. Okay, now we can remove clutter in the GPR radiograms. So next, we are going to talk about how we can use the reflection signatures in the radiogram to characterize subsurface objects. We've been working on two projects. One is to use GPR to detect and evaluate corrosion damage in reinforcing bars in concrete infrastructures. And another one is to detect and map tree roots for tree preservation. So we've been working on using GPR to estimate the diameter of metal bars in concrete and estimate multiple K-tree root parameters. So first we'll talk about how to use GPR to estimate diameters of metal bars, and then we'll move on to talk about the tree root parameter estimations. GPR has been a great tool to detect reinforcing bars in concrete, because we know metal is a great reflector, it's a total reflector, right? But how to quantify the metal bar size has been a very challenging task. You probably want to know why should they estimate the size of the metal bar? Well, the thing is that the corrosion induces cross-section reduction of metal bar. So if we could precisely measure the metal bar's size embedded in the concrete infrastructures, we can use it as an indicator to assess the corrosion damage level of the reinforced concrete structures. So how can we precisely measure the diameter of the metal bar? Well, we have developed two methods to achieve that. The first method is based on the radial cross-section theory. So we call it a radial cross-section method. For this method, we know that metal bars will reflect electromagnetic waves, but metal bars with different diameters respond differently to electromagnetic waves with different polarizations. So for example, if we use an enhanced system with polarization that is parallel to metal bar's orientation to detect this metal bar, we can receive pretty strong reflected signal from the metal bar due to polarization match. But if you're going to use an enhanced system with polarizations at perpendicular to the metal bar's orientation to detect the metal bar, we'll say that reflected signal from the metal bar is much weaker compared to the parallel polarized case, right? So what we want to do in our work is that we want to establish the relationship between the diameter of the metal bar to the ratio of the reflected power in these two dual polarized internal cases. And then if we could establish this relationship, we can use the power ratio to derive the metal bar's diameter in real measurements, right? So our method is like this. If we only use one polarized antenna to detect the reflection from the metal bar, For example, we use antenna with polarization that is parallel to metal bar's orientation to detect this metal bar. We know that the reflected power of this metal bar is governed by the well-established rate equation, as we mentioned earlier, is a complex function of multiple system parameters, the signal loss along the propagation path, and on the air to concrete surface, and the scattering base of the metal bar. The scattering base of metal bar is directly associated with the diameter of the metal bar. So you might think, well, seems like we can use this acquired power to directly characterize the metal bar's diameter, right? But the challenge is that in real cases, there are so many system parameters that are hard to be precisely quantified. But don't worry, we can introduce an antenna with a different polarization, the perpendicular polarization, to acquire the metal bar's reflected signal. And in this case, the reflected signal from the metal bar is also governed by the same Rayleigh equation shown here, while the only difference is the scattering base of the metal bar is to this perpendicular polarization, right? So if we use the same antenna system, if we use the same GPR system and just rotate this antenna by 90 degrees, then we can say that all the system and all these other parameters can be eliminated by taking the ratio of the received power using these two systems. So the power ratio is equal to the scattering base ratio at a single frequency. And the scattering base for perpendicular and parallel polarization of an cylindrical metal bar has been well derived in the Rayleigh field, which are shown here. They are directly related to the diameter of the metal bar, which is the A shown here. So combine these equations, we have successfully built the relation between the power ratio at a single frequency with the metal bar's radius or diameter. But when you think about ground-penetrating radar, it's a wideband device. So it's not very feasible to use a single frequency to characterize a wideband performance. It's more, sorry, I'm not sure why the equation is shown here, but it's more easier and more robust to use the ratio of the maximum power collected by these two antenna systems in the time domain to characterize the metal bar's radius. So we further incorporate inverse Fourier transform and broaden this power ratio relation to the wideband power ratio relation. So what we've done here is that we build a relation between the peak power ratio acquired by these two antenna systems with the metal bar's radius, as shown in this equation shown here. We won't go into the mathematical details shown here due to time limit. But once we have this relation, we can use this relation plus the power ratio acquired in the measurement to characterize the metal bar's diameter. In our experiment, we have used our self-designed dual-polarized valve antenna operate across a broadband from 0.5 GHz up to 3 GHz to detect the reflected signal from the metal bar, calculate the peak power ratio, and then use this equation to derive the metal bar's radius or diameter. We have conducted numerous simulations and experiments to verify the performance of our methods. And here we show the estimated result in 8 different metal bar cases. The metal bars are with different diameters. From these images, we can say that the estimated diameter agree very well with the real diameter of the metal bar. And the estimation error is well below 10%. It's below 6% in different cases. So this provides a method to well characterize the metal bar size. But you might notice that this is a numerical-based method. So later on, my collaborator, Dr. Wei Xiacheng from Nanyang Technological University, she suggested that can we combine the imaging algorithm with metal bar sizing to provide a more intuitive understanding of the metal bar? So we can say the Malabar and know the size, right? So later on, we carried out another work where we use a linear antenna array with 15 Vivaldi antenna elements to acquire the reflex signal from the Malabar. Basically, we acquired 15 by 15 full matrix array data for each Malabar. And then we adopt the conventional imaging algorithm, which is the delay and sum imaging algorithm, to produce the high-resolution imaging of this Malabar. And then we measure the 3 dB coordinates of this image and further correlate it with the Malabar's diameter. Here we show the imaging results of the 3 Malabars in the concrete and the estimated diameters in these 3 cases. We can see that compared to the ground truth diameter of the Malabars, we can well estimate the diameter of the Malabar with errors well below 10%. In the 3 cases, the errors are below 5%. So these methods provide more intuitive understanding of Malabar because we can say the imaging result of Malabar and we can know the diameter of the Malabar. We have further implemented these methods to monitor the entire corrosion process of the reinforcement bars in concrete. And we found out that the imaging results of this array is highly sensitive to subtle change, to very minor change of Malabar in the corrosion process. And we are currently working on advancing these methods to really provide indication of the corrosion damage level in the reinforced concrete infrastructures. Well, these are the 2 works related to characterize Malabar, the size of Malabar in our research. And now we are going to move to talk about how can we characterize the tree roots, the parameters of tree roots. So we are going to move from civil engineering to environmental engineering. Well, different from Malabars in concrete, where we know the material property, we can consider it as a perfect electric conductor without causing much trouble. And in the reinforced concrete structures, the orientation of the Malabar is usually well planned. But for tree roots, the scenarios is much more complicated because the tree root reflection intergram is a complex function of multiple tree root parameters, including the root depth, diameter, permittivity, and the orientation angles. Conventional methods can only estimate 1 parameters at a time without considering other parameters, so they have limited accuracy in estimating each tree root parameters. In our work, we aim to simultaneously derive the 5 tree root parameters so that we can further facilitate further mapping of the tree root and the health examination of the tree root. But first, tree root as an elongated object depolarize electromagnetic waves based on different orientations, right? So to guarantee the well detection capability of tree root, we first use our self-designed depolarized antennas together with a vector analyzer to collect 4 parametric radargrams shown here. The 4 parametric radargram greatly improve the detection capability of tree roots in different scenarios. And then we derived a convolutional neural network architecture to build the nonlinear relation between these root reflection signatures in the multiple metric radiograms and the 5 tree root parameters, including the depth, diameter, permittivity, and horizontal and vertical orientation angles. This work was done before my clutter removal task, clutter removal work. So in this work, I kind of adopted a different approach to remove clutter. I devised a neural network model which composed of a mask net which kind of highlights the root reflected area, and then use this highlighted area as a guidance to extract and integrate key features of the root reflected areas, and then build those features with the 5 tree root parameters, which is achieved in the second subnetwork, which we call it a parameter network. Of course, we have done both simulations and measurement to collect data to train this neural network model. And once we train this neural network model, we have used it to estimate 50 root parameters. And we can say that here shows the estimation error in 50 real root cases. We can say that our well-trained neural network is capable of well-estimate each root parameters with high accuracy. And those well-estimated parameters greatly facilitate further mapping of the tree root system. Okay, now we have seen that we can use convolutional neural network to address the challenging clutter removal task and the challenging parameter estimation task. Then my collaborator, Dr. Qixi Dai, who was a PhD student in our group, and then she's currently a postdoc at National University of Singapore. So she suggested that is it possible to use neural network architecture to build the inverse scattering relationship between the GPR scan and the three-dimensional subsurface permittivity distribution. And if we could build that relationship, we can use neural network to produce high-resolution imaging result of the subsurface object, right? And we think we can do that. So we conducted a feasibility study. We derived a two-stage neural network model, including the first stage is devoted to remove clutter in the GPR scans, and the second stage of the neural network build the inverse scattering relation between the noise scan with the three-dimensional subsurface permittivity distribution. To train the neural network, we have conducted many field experiments to collect three-dimensional scans of different objects with different properties at different positions. Once we well-train this neural network, we have examined its performance in our sand soil for the object in our sand soil. And some of the results in our preliminary study are shown here. Now, the first rule shows the ground truth image and ground truth subsurface permittivity distributions of the subsurface objects, while the second rule shows the estimated results using our three-dimensional neural network. We can say that our neural network is capable of reconstruct the shape, size, position, and permittivity distribution of subsurface object with relatively good accuracy. Although the neural network can still produce some environmental clutter, and the edge of this object reflection is slightly blurry. But in this feasibility study, we have witnessed the capability of this neural network structure to well restore the subsurface object. We have to admit that this work in the current stage lack generalizability because it's a data-driven method, and the performance is confined to the domain of the data that we train this neural network. But the promising result in our feasibility study motivated us to further explore, to further advance the neural network architectures and incorporate the physics priors to further improve the imaging results. So here is a brief summary of our GPR research so far. I would say our research is highly interdisciplinary. It involves intelligent designs, the innovation of new methods, and the advancement of both conventional and deep learning data process algorithms to advance the GPR technologies. As a pioneer attempt, we have leveraged the feature extraction and learning capabilities of neural network to address challenging GPR tasks, including clutter removal in GPR radargrams, parameter estimation of subsurface targets, and the high-resolution imaging of subsurface structures. Here I want to highlight that although we have demonstrated the strong capability of neural network architectures to address these challenging GPR tasks, I would say this research topic is still in its infancy. We face many challenges like lack of standard open source reader dataset, and we need to further improve neural network models to improve the generalizability of these models in diverse subsurface environment. So there are so much to improve and to work on in the future. If you are interested in our work, all of our GPR work and non-destructive testing work can be found in my homepage shown here. We also released all the code and dataset in our deep learning work. We hope this open source code and dataset will help researchers in the future, researchers to further develop GPR technologies in the future. So if you are interested in our work or if you have any questions related to that, please feel free to reach out. Before I conclude my presentation, I would like to thank my wonderful collaborators at Nanyang Technical University for their support in this work. And this concludes my presentation. I'm very happy to answer any questions that you may have. Thank you.
Thank you, ma'am. Thank you for the amazing talk. And yes, ma'am, we have few questions in the chat box that I would like to take up with permission.
Sure.
Yeah. The first question is from Praveen Mali. The question is advantages of CNN-based clutter removal over time grading.
Yeah. Okay. This is a great question. I didn't show the slides here, but I do have a slides. Okay. Can you say the slides shown here? Sorry. Hang on.
Yeah, I need,
sorry. I need to reshare my slides because I'm
right.
switching to another presentation. Okay. Okay, could you say this?
Yes, ma'am.
Okay, sure. This is a great question. We have compared the performance of our CNN-based clutter removal network with conventional methods, including the mean subtraction and singular value decomposition method. And you can say that in this case, the conventional clutter removal methods still leave residue clutter that merged with subsurface fractions due to the irregularity of the subsurface clutter distribution. But our CNN-based neural network is capable of successfully remove all the clutters and restore the target responses. So based on the visualized result, we can obviously see the advantage of our CNN-based neural network. Well, we also compare the performance numerically, and you can say that compared to the conventional methods, our network achieves much better performance. It greatly resembles the ground truth clutter-free images shown here, and the mean absolute error is much lower than conventional methods. So we have actually conducted extensive study to compare the network performance with all of the conventional clutter removal methods, and we have verified that the CNN-based work achieved the best performance. Thank you.
Thank you, ma'am. I think that answers the question. The next question is by Anil Kumar. The question is, what are the frequency band used for GPR antenna design?
Okay, this is a great question. I would say it depends on the applications it depends on what depths you want to penetrate beneath the surface and the subsurface material property. If it's lossy material, you definitely need to shift your frequency band to much lower frequencies. But if you only want to, for example, detect metal bars in concrete buildings where the depth of metal bar is only like few centimeters, then you can use much higher GPR antennas. Well, in our work, for our tree root study, well, the root usually located within 1.5 meter beneath the soil surface, and we conducted this work in Singapore, which the soil is have higher moisture level, so it's pretty lossy. So the frequency for the GPR antennas we designed operates from 0.2 gigahertz up to 4 gigahertz. Okay, but for the concrete building study, for the metal bar study, as I mentioned, the metal bar is the position of metal bar is very shallow. We can adopt antennas ranging from 1 gigahertz to 6 gigahertz for that study. So the frequency definitely depends on the application that you want to work on.
Right, ma'am. Thank you.
Thank you.
The next question is by Ardhendu. The question is, please elaborate more on time-gated signal processing of wideband GPR data for high-resolution imaging.
Sorry, could you repeat the question one more
Yes, ma'am.
time?
The question is, please elaborate more on time-gated signal processing of wideband GPR data for high-resolution imaging.
High resolution imaging. Are you referring to day's work or day's work?
I think he's referring for time-gated signal processing, ma'am.
Could the audience kind of elaborate the question a bit more?
Yes, ma'am. I think we can meanwhile take the next question while if we can clarify the question.
Okay, sure. I'll briefly clarify the. I'll answer this question based on my understanding. Okay, so for example, in this work, why we adopt wideband signal is that wideband signal in the time domain corresponds to a very narrow pulse, right? And very narrow pulse allow us to achieve much higher resolution when we detect the signal, because it can well differentiate two objects that is very close to each other, right? We have some fundamental physics that governs this relation. So basically, the wider the signal is, the narrower the pulse is in the time domain. And the narrower the pulse is, the higher resolution is when we detect the object. And the higher resolution is the better imaging that we can achieve in our applications. Yeah. If you have follow-up questions, definitely let me know.
Sure.
Thank you.
Ma'am, the next question is by Ankita. The question is a bit large. The question is, while using the ultra-wideband transmitter antenna for GPR, for the scenarios of uneven surface, the radiation pattern changes depending on the material properties of the ground and also due to multipath effect. This pattern variation will also be different for different frequencies. How it will affect the detection accuracy of the GPR system? If the effect is severe, how is it taken care of?
Is it possible that I can say the questions here?
Yes, ma'am. It will be better.
Is it? Oh, okay. I saw the chat box here. Okay. Let me. It. Let me find the questions right here.
Yeah, it is by Ankita, ma'am. Ankita Vishwas.
Yeah. This primary. Yeah. It is a good question. Yeah, I would say the main challenge when in GP application is that irregularity and the complex subsurface medium distribution. And in our work, we adopted ground-coupled GPR. So basically, our GPR operates just beneath the soil or the surface. So most of the electromagnetic wave can penetrate inside the subsurface medium and then can well detect the object. Although the subsurface is complex and irregular, as long as we can as long as we can well design the antenna to well couple the signals into the subsurface material, and then as long as we can well collect the reflex signal, we can always adopt the percent algorithm to further correct the data, for example, to remove clutter and to correct the irregular data in the GPR radargram, and then these are called like pre-processing steps, and then we can move to the GPR data processing for example, parameter estimation and imaging. Yeah, thank you.
Right, ma'am. Thank you. Ma'am, the next question is by Pankaj Chawla.
Sorry, next question is?
Yes, ma'am. The next question is by Pankaj Chawla. The question is, in slide 14, gamma is personifying reflection cutoff.
Slide 14. We switch to the slide 14. Am I missing some slides from here? The gamma is are you I guess the questions is related to this work. So gamma is reflection coefficient?
Yeah, the tilde part into that particular power from that perpendicular polarization. What would be that signify, sir?
Yeah. This one, right? Yes.
Yeah,
It
yeah.
corresponds to the reflection coefficient at the air to concrete surface. Yeah. We have. No. Sorry. This is not reflection coefficient. This is transmission coefficient because the signals transmit into the concrete and then transmit back. So these are the transmission coefficient. Our next question is explain about front-end requirements of the GPR, what's the power, the rise time required, nodes. Okay, so in our lab equipment, in our lab experiment, we kind of like adopted a very let me find the picture, a simplified GPR structure shown here, where we used vector network analyzer to connect with antennas of different characteristics for subsurface sensing application. The GPR can like sweep the frequencies across a wide band, so we generally regard this system as step frequency continuous wave system. Why we adopt this design instead of designing circuits integrated with our antenna is that we actually worked on many different applications where different applications can like respond to different frequencies. So we want to leverage the wideband capability of ultrawide of vector network analyzer and connect it to different antennas for different applications. So in our research, we used VNA for that purpose. And for the power, there are regulations that limit the power that we can send out using ground-penetrating radar, because we don't want to interfere with other communications, for example, mobile communication, because bands sometimes overlap with each other, right? So the the output power in our system is below 0 dBm. Mostly work is 0 dBm or by 5 dBm. Yeah, thank you.
Thank you, ma'am. The next question is by Shyam Sundar Josh.
What frequency band will be plastic body? Yeah. Okay. This question is great, and this question is similar to the one that I mentioned earlier. What frequency band depends on multiple factors, because if we look at the real equation shown here, right? You can say the reflected power is a compact function of so many factors. If it's a plastic material, if it's a plastic material embedded in a dry soil, if your plastic material, for example, the permittivity, the relative permittivity is only like, for example, 6, and the dry soil permittivity is around 3 to 4, I would say the reflection coefficient is pretty small, or the so basically the object real cross section will be relatively small, and in this case you will need to improve your GPR system. For example, lower the frequencies or increase the gain of your antenna to achieve better detection capability. It definitely depends on the size, the permittivity of your plastic body, because it governs the object radial cross-section. Yeah, I would suggest conduct some feasibility study in your lab first before you really finalize your GPR system design. Okay. Next question, how to model soil distribution in simulation. This is a great question. I have a wonderful software, which is open source software that I would like to recommend. It is called GPR Max. It's GPR Max Real. It's GPR Max. It's an open source simulation software, which allow you to generate kind of like different cells in the subsurface domain, and you can assign different properties to different cells to model the heterogeneous property of subsurface medium. So I would definitely recommend you to download it, give it a try. It's just a wonderful simulation software. Next question, how much depth can you achieve with 0 dB? Yeah. Again, this question depends on the subsurface material property and your antenna gain, right? Your antenna directivity. Generally speaking, in our study, we successfully achieve our antenna has pretty high gain, around 5 to 10 dBm, and with that system, we are able, and we have wideband signal, right, ranging from 0.2 up to 3 gigahertz and above. And in our different applications, we can successfully achieve depths around at least 1 meter in different applications. Yeah, generally speaking, but well, the capability definitely differs for different subsurface medium.
Thank you, ma'am. Ma'am, I have a question of my own.
Sure.
What is the effect of moisture? Because that varies with different roof season and area. So how do we train the neural network for this kind of specifications? Also, I saw the neural network subset where two standard subsets are considered, sand and concrete. So is there any option of selecting water in that scenario?
Definitely. This is a great question. It's like, well, neural network is, as I mentioned, is a data-driven method, right? So if you want that neural network to work well with no matter soil or concrete with different moisture levels, you'll definitely need to incorporate these moisture levels into your data set, into your training data set. So that's why I said the software I just mentioned is a great software because you can actually define, well, there are some kind of like mature, well-established relationship between moisture level of different materials with their debye parameters. And that software is able to incorporate that debye parameters in the simulation. So basically, you can simulate the object responses in surface material with different moisture level, and then you use it as your training data. You incorporate the variation of, then you can incorporate the variation of moisture level into the consideration when you train the neural network. Yeah, this is a wonderful question. Thank you.
Thank you, ma'am. Ma'am, any real current work that is your group is doing regarding this technology on GPR currently?
Sorry, could you
Any
repeat the question?
means current projects or any work that your group is currently doing, like regarding GPR
Yeah,
currently?
this is this is the wonderful question. So currently I'm a first year assistant professor, and my two PhD students will join our group in the upcoming fall. So currently I only have undergraduate research.